Today we're going to do a quick review of the graphs of exponential and logarithmic functions. We're going to take a look first at exponential functions and take a look at functions whose base are greater than 1 and understand some about the general shape and common points and asymptotes for those. And then we'll also look for b-values that are between 0 and 1. Once we get a handle on that, we'll take a look at logarithmic functions with the same premise where we have b-values either greater than 1 or between 0 and 1. See what we can find that they have in common. So let's look first at a simple exponential graph, 2 to the x, and let's take a look and see if we can figure out how this graph gets its shape. So when we start, we'll take a look at 2 to the x, and we can just kind of think of this point here as what we get if we plug in 0. If I plug in 0 for x, this is 2 to the 0. That's this height. If I plug in 1 for x, we get 2 to the 1. And so on. If I plug in 2 for my exponent, this distance here is 2 squared. So you can see the shape of this graph looking like growth. As we move to the left and we put in exponents that are smaller and smaller, for example, if we put in -1, then I have 2 to the -1, which is also 1/2. Now, if we keep progressing to the left, we're going to see these values get smaller and smaller and smaller the larger the exponent that we put in here. But it's never going to reach 0. So what we're going to see is we're going to see that we have an asymptote on this graph. Because on the left here, these values are going to get closer and closer to 0, but never reach it. Okay, so there's our horizontal asymptote. We can see the general shape of the graph. If we take a look now at 3 to the x, so let's go ahead and look at 3 to the x. And there we go. So 3 to the x, we can see it's got the same y-intercept. And if we're looking at that, it's pretty clear to see why that is, because that's going to be 3 to the 0. 3 to the 0. The difference is now this point here on this graph is not over 1 up 2, it's now over 1 up 3, because that is 3 to the 1. Let's check out 4 to the x. Same idea. Same y-intercept, slightly different value here when we look at what happens when we plug in 1, right? When we go and plug in 1, we're going to get this right here, and that distance is 4 to the 1. Now notice if we look at these graphs, they all have the same asymptote that's horizontal here, and it looks like y equals 0. So let's go ahead and see if we can identify some things that would be really helpful if we were graphing an exponential function with a b-value greater than 1, but that is so all the graphs that we just looked at, they share the same horizontal asymptote, regardless of what the base is. So let's make a little sketch. And so what we've got is we have a graph that has a horizontal asymptote, no matter what the base is, of y equals 0. So we can say we've got a horizontal asymptote of y equals 0. And then all of those graphs, regardless of base, shared the first point right here, which was 0, 1. And that's because if we plug in 0 for x, we are going to get 1. They also had another point that they sort of shared, depending on their base, where if we plug in 1 for our x value, we just get that base. So we can think of that next nice point as 1, b. And if you know these things, this can help you sketch a graph. A couple good points plus the asymptote helps you understand what your graph should look like. If we now go ahead and turn back to Desmos and let's look at some graphs that have b-values that are now less than 1. So take a look at these. We'll remove these and add in a couple that have b-values that are less than 1. So as you notice, the graph has a similar shape, but takes on a different sort of look in that it is decreasing. So these are exponential decay. And you can kind of see how they're related to their counterparts with b values that are greater than 1. They look like reflections across the x-axis. But they still maintain the same basic features, which is to say that what they can do is have the same y-intercept of 0, 1, and then they also have the same second point, which would be 1, and then whatever your b value is. In this case, that's a half. They still have a horizontal asymptote of y equals 0. Really, the only substantial difference is that instead of this graph increasing from negative infinity to positive infinity, it's actually decreasing. So let's go ahead and do a quick sketch of that as well. Same deal. We've got our horizontal asymptote, y equals 0. Same y-intercept of 0, 1. The only difference this time is that next point that we put on the graph that's 1b is going to be over 1, and it's going to be down. It's going to be decreasing. So 1b. And so then we can see this exponential decay here. So they share these points of 0, 1, 1b, horizontal asymptote of y equals 0. A couple other features that they share are their domain and range. So the domain and range for both of these, domain is all real numbers. We can plug in any number we want to that exponent. And then the range is 0 to infinity. All right, so let's continue by looking at logarithmic graphs. We'll start again with b values that are greater than 1, and then we'll talk about b values that are between 0 and 1. So let's check out Desmos, and let's start with log base 2 of x. And we can see this graph sort of clearly. We've got another curve happening, but it's looking different than our exponential graph. And let's put a couple more on here so we can maybe see some commonalities that they have. So when we put on the log base 3 of x, we can see this graph here, start to see what they share. They seem to share an x-intercept, which is true for log base 4. And if we look sort of zoomed out a little bit, we can see that they also share what looks to be a vertical asymptote. And so when we're looking at these, we can understand a few key points on them clearly. So as we look at this, we said we can see this vertical asymptote here of x equals 0, where this graph is going to approach 0 but never reach it. And then we see that they share a common point this time. They all share this value of 1, 0 as an intercept. And then we can look at each of these, and depending on their base, we have this point here for log base 2, this point here for log base 3, this point here for log base 4. All of these distances are related to the base. So since this is base 2, we can see this distance here is 2. We've got this one here is 3, and this one here is 4. So now let's see what we can do to kind of identify these common features and understand how to graph a log function with any base. All right, so let's go ahead and sketch a graph, keeping in mind that now with our log function, we had a vertical asymptote. So we've got a boundary on this graph, and we have a vertical asymptote of x equals 0. And this time we have a nice point, an x-intercept of 1, 0. And we also have another nice point on this graph, which is going to be somewhere over here, and that value is going to be b, comma 1. So as we see this graph materialize, we see our vertical asymptote rather, and we have a nice point of 1, 0, and another good point of b, comma 1. Now what you might notice if you're looking at the exponential function on your left and this one on the right is there seems to be something going on here with those values. And if you remember from Algebra 2, exponential functions and logarithmic functions are inverses of each other. And so when you look at these graphs, all the values are inverted. So when we look at this, these are inverses of each other, which simply means that the x and y values are switched. So if you look at the coordinates that we chose as our common points, 0, 1 on the exponential, that becomes 1, 0 on the logarithmic. The horizontal asymptote of y equals 0 on the logarithm becomes x equals 0, and a vertical asymptote. As we continue to compare this exponential and this log function where the b value is greater than 1, the other thing that we can see is that while they're different functions, they both represent growth, or they have increasing values over their entire interval. That's going to be a little bit different than the ones we see below where the b value is less than 1. We're going to see decay. So let's take a look at a sketch for b values less than 1, and we'll take a quick look at Desmos first. So in looking at this graph, we can see that we've got a nice point right here at 1, 0, just like our other logarithmic function. And then we've got a nice point on each graph, looking, for example, at log where the base is 1/2, where we've got, this is 1/2, comma 1. 1/2 is the base, so that's the base, comma 1. If we look at the log where the base is 1/4, same thing is happening there. We've got our base, which is 1/4, and 1. That's not showing up very well. 1/4, comma 1. So in both of these cases, it's not writing very nicely, but the idea is it's b, comma 1. So let's go ahead and put this on our notes so we can understand it a little more clearly. All right, so we will start by sketching our xy axis. We noted that we're still going to have a vertical asymptote. That's going to be the same, x equals 0. We're going to have our same point of 1, 0 for our x-intercept. And this time what we're going to see, since our base is something smaller than 1, we're going to see this be somewhere closer to the asymptote. So base, comma 1. And so then we'll see our graph take this sort of shape. All right, last what I want to do is let's take a look and understand our domain and range for these functions here, for both of the logarithmic functions, regardless of whether the b value is bigger than 1 or between 0 and 1. We have a domain that goes from 0 to infinity because we have that vertical asymptote as a stopping point. But our range is all real numbers. And something to keep in mind there is that is all part of these being inverses of each other. The domain and range of exponential functions and logarithmic functions are inverted. The domain switches with the range, and the range switches with the domain. So now what you're going to want to do is try and take these basic points and understandings about exponential functions and logarithmic functions and see if you can sketch these functions below. So I want you to identify their transformations, their base, whether they're exponential and logarithmic, and see if you can graph these with a couple key points. We'll show those on a separate video.